All right, so we're talking about game theory. The prisoner's dilemma was the fancy thing that we ended on. We learned that it doesn't make sense, but at the same time it does. We're going to find a Nash equilibrium where both of those prisoners are kind of bound to confess because they can't really control what the other prisoner does. It's a non-cooperative game, and so they're better off in the long run, on average, by confessing. So that's kind of fun. Let's talk about some other kinds of games that, again, remember that the definition is very vague. One that maybe you've played with a sibling before is cutting a cake or sharing something with somebody. All right, so the internet won't tell me if this is cooperative or non-cooperative. I guess it maybe depends. Like, you're kind of forced to cooperate by like your parent or something, so it's a little bit of a gray area. Remember that cooperative game theory? That means you're studying things where forming alliances is a good thing. Equals good. I guess either way it goes, you're kind of forced to be in an alliance for this cake cutting game. So have you ever played this with a sibling before? Like, if one person cuts the cake, then it's the other person's job to pick like which piece they want. Have we seen that before? If we're not an only child, maybe. So that is a game, of course. You can model it as one. And so what's the optimal strategy for this game? You always want to cut the cake in half, right? Like, here's your cake, and you get to share it with your sibling. And so it's always best to cut it straight in half, because when your sibling picks after you cut, they're always going to pick the bigger half. If there isn't a bigger half, you're going to get at most, right? At most half the cake. So you might as well do it right. Because if you mess up, right, if you try to take advantage of your younger sibling, for example, and you try to cut the cake like this, you know that you're going to be stuck when your sibling gets to pick, right? They're going to pick the big piece, and you're going to be stuck with the smaller one. So it's always in your best interest to play it fair, yeah? So that's technically a game. And we can talk about a fun new topic in relation to this idea. Let's call it, this topic is called Pareto optimality. It's another fun thing, just like Nash equilibriums, that comes up a whole lot. Excuse me. That comes up a whole lot when you are studying game theory. So Pareto optimality is talking about you are setting aside stuff. You're allocating some resources, like you're allocating some cake slices. And a resource allocation is said to be Pareto optimal when, if you were to change that allocation, somebody is always worse off. So it's a very utilitarian kind of concept, which is fun. So let's talk about some Pareto optimal allocations for cake cutting. It's when something is Pareto optimal, and if you were to change that allocation, then it would leave somebody worse off. So cutting the cake in half is optimal. You see that? Cutting the cake in half is Pareto optimal because, according to the definition, do you see how if you were to change how you cut that cake, like maybe you cut it like this instead, boop, and then you have two halves like that. Let me make it bigger. It always messes up my pen at the start. Sorry. If you did it like this instead, boop, you get a little bit bigger of one side and a little bit smaller of another side. That's going to leave somebody worse off, right? Whoever gets this piece. See that? If you changed it, somebody would be worse off. So cutting the cake in half is a Pareto optimal allocation. So that's kind of maybe a reason why that's the choice you want to make. But actually, according to this definition, every cake cutting allocation is Pareto optimal. So maybe it's not the best example at the same time. But it usually feels right when something's Pareto optimal. This is just an interesting example where it also breaks down too. So like if you made this cake cutting allocation, right? Do you see how if you were to change that, again, following the definition of this silly term, if you were to change this allocation to be more like this instead, do you see how somebody's getting less cake, like whoever was getting this big piece before now has less of a big piece? So somebody's worse off. So this is also Pareto optimal, interestingly enough. But usually it means something that sounds nice in our minds. And this is the term that we can use to finally explain away why the prisoner's dilemma didn't make so much sense, why it was so confusing in our minds. It's because the Nash equilibrium that we discovered, that the prisoners are going to want to confess most times, all the time, that Nash equilibrium, that thing that they're going to want to do, is not Pareto optimal. And that helps like explain why it seems so backwards in our minds, because we are maybe programmed in our brains to like Pareto optimal things. But do you see how this is not a Pareto optimal allocation? There is a path forward, this one right here, where you make a change and people are all better off. You see that? So that is a nice term to use here, even if it's a little confusing. The reason why this is so backwards in our minds, this prisoner's dilemma game, and why they're going to pick this one seems so wrong, it's because it's not Pareto optimal. All right, so that's a term that we can use to describe our confusion. Any questions about that? So I just want to teach you a few key terms that maybe you'll see again if you study game theory further. All right, so that's that one. Let's next talk about a fun topic called fare taxi ride. So if you're ever sharing like an Uber with somebody, this is exactly how you calculate how to split the bill. Maybe the app does it already, who knows. But this is a cooperative game, people sharing a taxi or sharing a ride share, Lyft or Uber. So this is, first of all, a cooperative game. You want to share a taxi to save money, right? And so here's the setup. You got two people, let's say person A, person B, Alice and Bob. They're going to share a taxi, and Alice lives on the way to Bob's house. She lives a bit closer. So here's my best drawing of a taxi. Boop, boop. And here's the route that it's going to take. Like on the way home, like here's Bob's house here. Alice lives about, I don't know, here. Something like that. So that's the route. And so obviously they should get in the taxi together so they can split the bill. All right. So here's the setup. Here's how you calculate the fairest way to split the bill, which is fun to think about. So useful information coming out of game theory here. How to play this cooperative game of sharing a taxi. So if Alice, if she got a taxi by herself, she's not going too far, so it would be $5, let's say, to get her to her house. But if Bob got a taxi by himself, he would pay $12, right? He would pay $12, and that would be that, because it's farther, okay? So the fare for both of them, because they are going to Bob's house in the end, and just like stopping for a split second at Alice's place, the fare is still $12 if they both share the taxi, all right? So how are they going to split that $12 fairly? That's the game, all right? So the way to calculate the most fair fare, if that makes sense, is to compute what's called the Shapley value. That's another term that comes up a lot. So if we compute whatever that is, it will tell us the answer. And the way that you compute it is to consider all the waves of who pays first. And let me say that in just a second. First of all, because the fare is $12, it's not fair to pay like $6 each. Like $6 and $6 is not fair. That's a great deal for Bob, though, because if Alice might as well have gotten a taxi herself if she's going to pay $6 to go to somewhere that would have taken her $5 otherwise. So that's definitely not fair. We need to fix that. All right, so here's how you do it. You calculate the Shapley value by considering all the different permutations of, so that's the orderings, of who's going to pay the bill first. And then the person who's left gets to pay the rest. And then we're going to take the average again, just like we did for the prisoner's dilemma problem. So this doesn't really make sense. Consider the permutations of who pays the remaining bill. Let me break this down. So these are the two orders, right, in which the bill could be paid. Either Alice pays first and then Bob, or Bob pays first and then Alice pays too. All right? I hope that makes at least enough sense. And so the game that we're going to play here is Alice is going to pay however much she would normally pay in this situation. She would pay $5 because she pays first, and that's her fare. And then the total fare is $12, so Bob's going to pay whatever's left, right, in this example universe. We're going to consider every example universe. So there's $7 left of those 12. So Bob would pay $7 if Alice paid the full bill first. Otherwise, if Bob paid his fare first, right, he would normally pay $12. So he would pay $12. And then Alice, because the whole total is $12, Alice would pay $0 in that situation, right? If Bob were forced to pay first. And so these are the two universes, right? The two possibilities of who pays first. And now what we do is we consider it from one person's perspective. It's symmetric again. Let's consider it from Alice's perspective. What is the average cost that Alice would pay in each of these universes, each of these permutations, these situations. Alice's cost. Boop. So, on average, in this situation, she would be paying $5. And in this situation, she'd be paying $0 if Bob was nice enough to pay first. And so what we do is we compute the average, and that's called the Shapley value. What's the average for Alice to pay in these two situations? It's $2.50, and that ends up being the optimal fare for Alice to pay. That's the fairest fare. So Alice would pay $2.50, and then Bob would pay $9.50, and that would be the fair way to split the bill. All right, so that's how you calculate that. And now you know, if you ever share an Uber with somebody, now you know exactly how much to have them pay you back if they live on the way home. Any questions about that? So it's all about averages and all the possibilities, just like it was for the prisoner's dilemma. That's how we solved that problem too. So there's a lot of math involved, and we like to throw that math at computers. We love game theory. All right, let's keep in computer scientists with jobs, I guess. So yeah, if we're happy with that, I have another example that I think is going to take 3 slides to do. I want to teach you a way to solve a game. So let's solve tic-tac-toe. Let's solve the most optimal way to play this. This is finally a game that we define as a game in our minds. So I'm going to show you an algorithm called Minimax, which is a cute name, and it's a way to find the optimal strategy to play a real game, like one that has moves like this. All right? Minimax is a kind of searching through the space of all the ways you could play the game, and it's going to discover the optimal strategy. It'll tell you exactly what you should do to win, to give yourself the highest chance of winning at least. All right? So imagine that this is the game board right now, and you're like, and we're X, and it's our turn, because X goes first. So it's X's turn right now, and this is what the game board looks like. How would you discover, how could we programmatically discover that, like, this is definitely the best move to make right now, yeah, and win the game? How would you discover that? So what you do is you simulate, given your initial state that you care about, you simulate the game in its entirety. You can, tic-tac-toe is small enough to talk about every different possibility. So like, all right, maybe if X moves to this spot, the game will look like this. Or maybe X could go over here. Or maybe X would go over here and it will look like this or this or this. So you got a bunch of options. And then you just keep on expanding those options. All right, X moved. O could go here after that. O could go here after that. O could go here after that. So many options for O after that one. Or here are some more options for O if X made this move, etc., etc., etc. But you keep switching off X and O, of course. And so you're simulating this game. And what Minimax is it's a combination of minimization and maximization, depending on whose turn it is, right? Because we're trying to be X and win. So when it's our turn, we want to make a move that maximizes our chance of winning. And then when we're trying to simulate our opponent's turn, this will all make sense with an example, I promise. We're getting there. Then when it's O's turn, for example, then what we're going to do is we're going to assume they're the best possible player and that they're going to try to minimize our chance of winning. And we're going to calculate the best move in the face of their best move, all right? So assume the opponent always makes the best move. That will give us the best strategy to play, even in the face of their expert playing style, okay? So that's the goal. We're going to simulate every possible way to do it, all right? So here's a task for you. Maybe get out a piece of paper and help the people next to you try this. Starting with this game state, can you make a chart for all the different ways that the game could be played out until somebody wins? All right, and let's pretend it's X's turn right now, and even fill in O's moves if you have time. But here's the idea: like starting from here, and if it's X's turn, one way that it could go is X could go right here, right? That's the spot for X. So let's fill that in. So the game could be played out, and like it looked like this: X O O O X X. X could have gone right here, and that's another valid game board. Does that make sense? X could go in a few other places, so fill in the rest. And then from here, it's O's turn. Do you see that? So then, all right, what would happen here? O could go here or here. So like you got 2 options there. Does that make sense? So try to fill in all of those, and I'll show you how to use the simulation, all these possibilities, to calculate the best move using the Minimax algorithm. So take a couple minutes to draw out the game state. Then I'll fill it in. I'll give you a head start of like 2 minutes, and then I'll do the rest. I'll show you how to use Minimax to solve for, like, yeah, you should do the bottom left move if you're X right now. It definitely gets a bit more complicated, though. But give that a try. See if you can write out how the rest of the game could be played. See if you can draw it out. So where else could X go? Here or here. You could take any open spot, right? So it looks like there's 3 options for this first level of moves. Alright, so there should be 3 moves down here. I guess I shouldn't have drawn a 4th thing, but potentially many options here. Many. Here's how it works. So starting with this one, XOO. And then OXX. I see. That looks right. Then there are 3 options for X to move. Go here, here, or here. So we're going to simulate the game. So we're going to try it every different way. See what happens. Try every different move. So, alright, X could have gone. See if I can copy and paste this easily. That saved me a whole lot of drawing. Oh, yeah. So it could have gone there, or there, or there. Oops. Boop. Interesting. Alright, so X could have gone here, or here, or here. So those are 3 different possibilities there. And then now it's O's turn. So O could go, for this case, here or here. So there's 2 possibilities from there. See how I'm doing that? So O could go either. I'm probably going to make this a little bit smaller. XOO, XO, XX, XOO, XO, XX. So O could either go here or here, there. And then, all right, what about, I guess let's continue. So here, still nobody's won. There's only one place that X could go after this, right? X could go here, here, here. Just fill in that last slot. See that? And X wins the game if that's the case. Otherwise, here O is 1. You see that? If O's done it that way. So we can stop the game. There's no more continuing after that one. So let's try this one. This one's already 1, so X is 1 here, so there's nothing left to explore. And then it's this one. All right, so it's O's turn. Where could O go? Either here or here. So let's draw that out. And this is what you would do as you're simulating. X, X, O, 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 X, X, X. So O could either go, let's see here, or here. If he goes here, he won. Otherwise, there's one more move for X to make, and then X wins. O, O, X, 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 X. All right. So, are there any questions about how I filled this out? That's what a computer would be doing. Figuring out every possible way that the game could be played until somebody wins or the game's over and it's a tie. But that's the goal. So you get down to all the last games, all the last moves, and then you start your way up. So here's what Minimax does. So again, it's going to maximize our chance of winning, and when it's the opponent's turn, we're going to assume that they're going to try to minimize our chance of winning. So you work your way up, and you assign numbers, because then we can do maximization and minimization on numbers. So here's the idea. So, all right, here, this is the end game for somebody. X1 here. This is the end game in O1. This is the end game in X1, end game and X1, and end game and O1. All right, so we're going to assign numbers based on our perspective. We're pretending we're X. So let's give some numbers to these ending states based on whether or not we won or lost. So if we win, let's say that's a good number. We want to be like +1, a good number for us. So +1 score for this game, +1 score for this game. Okay. If O ever wins, let's say we don't want that. We want to make sure that we don't have that happen. That's bad score for us, right? So we'll call that -1. -1. So for all those end game states, we give them numbers like that. And then the goal is we try to move up the possibilities. And so like when we're here, there's only one option. And so like what is the score for every possible outcome? The best score for us, it's going to be +1. We're kind of forced there. And then for this one, if it's our turn, right? This is O's turn. When we're right here, this is O's turn. And what is O going to do? It's going to try to minimize our chance of winning, so we know that O's going to pick this move. Does that make sense? That's how Minimax works. So the whole score for this part of the game is -1 if we made that move. So that's a bad one. We don't want to pick that one. You see how that's going to work? So here, this is X's move. It's going to try to maximize our score, so it'll take the max of every possibility. So the max is +1, because we do have a chance of winning. And then this one is, again, O's turn. When it's O's turn, they're going to try to minimize our chance of winning. So they're going to take the minimum outcome of the two possibilities. They're going to take the -1. And so we're going to score this as negative, which is not good for us. All right? So in the end, when it's our move at the very beginning, that's the thing that we really cared about, what move should we make right now? We can see that we're going to, as X, we want to maximize our chance of winning. And so we don't want to pick a -1 move, we want to pick a +1 move, because that leads to certain victory. So that's what the algorithm's going to notice, like, you better do this, okay? And this will work for, even when the game board doesn't look like this, it's like not as filled in as much, it'll still try to guide you towards one of the chances, or one of the outcomes where your chances of winning are pretty high, okay? But that's the algorithm in a nutshell. Any questions about that? So we can program computers to solve tic-tac-toe perfectly, because you can enumerate every possible move. You can always either tie or win, I guess. That's the idea. Okay, if we're all right with that, I would like to switch gears to a new set of slides, and we will continue. So this one is called recursion. I don't think we'll get time to get to the beauty part of it all, but recursion definitely. So let's talk about it. It's a very fun topic. It's a bit of a difficult topic, but it's so cool, right? So what recursion is, it's when you solve a problem in terms of that same problem, which sounds a bit like circular reasoning, right? It's like, oh, the thing is true because the thing is true. We know that that's a fallacy, right? So how would you ever hope to get at an answer? Well, here's the answer. There's a whole bunch of memes about this topic, by the way, because it's a harder topic. But why isn't it just circular reasoning to use the problem and solve it like that? That makes no sense. And again, my pens are broken. Let me fix them. Are you happy now? There we go. So is it not just circular reasoning to solve a problem in terms of itself? Yes and no. So these Russian stacking dolls are a great example of recursion in picture form. Like you have a biggest version of the problem, And inside of that, there's a slightly smaller version. Inside of that, there's a slightly smaller version, all the way until you get down to the baby tiny problem, the smallest version of the problem that you can immediately solve, right? The idea is that it needs to get smaller, all right? And so recursion is a way to do that. It's a way to solve a problem by solving smaller versions of the same problem. I promise this will make sense with an example, but we're getting there. It's like you're zooming in and seeing the same thing in a smaller way, and eventually you're going to stop, though, okay? That's the idea. There are some problems, like this one, if you've seen the Tower of Hanoi problem. It's a very standard example in recursion that you couldn't really do without this topic, this technique, right? So there's some things that you really can't do without recursion, so that's why I want to give you a little sneak peek about it. You'll learn a whole lot more about it if you take a major level computer science class. All right. So yeah, the answer is no. It is not circular reasoning as long as that problem gets smaller, all right? So the idea of recursion is you're trying to solve a problem in terms of smaller versions of itself, all right? That's the idea. So you have a problem, like here's your original problem. I'm trying to solve this problem that is this box, and it looks like this. Your goal, in recursion at least, is to find a problem, find that same box problem inside of itself. So find a smaller box that you can then hand off. So it looks like that. That's the idea. And then you use the solution to this smaller box to build the bigger box's answer, okay? So the smaller problem is called a sub-problem. Hopefully that makes sense. And we are going to use the answer to that sub-problem to solve the original, larger problem. All right? So with all that, let me give you the quintessential example of recursion, and then we'll code it up, and hopefully it will make sense. So I claim that finding the factorial of a number is a recursive problem. Do you all know what factorial is, right? It's that exclamation point in math. So 5 factorial equals 5 times 4 times 3 times 2 times 1. So take a couple minutes, discuss with the people sitting next to you. You don't have to write it down anywhere, but can you find a smaller factorial inside of 5 factorial? That's my main question for you now. Do you notice that same problem inside of itself? See if you can find it. Give me a minute to think about it. Pointing out to each other. Five factorial. It's 5 times 4 times 3 times 2 times 1. And so our goal is to define factorial in terms of itself. Alright, that's my timer. Did anybody find a smaller factorial? Any brave souls willing to share? What should I be circling? Where's a smaller factorial? Yeah. So what's 4 times 3 times 2 times 1 but 4 factorial? Does everybody see how 4 factorial is baked inside of 5 factorial? That's kind of interesting. The problem is inside of itself. And then, of course, there's also 3 factorial sitting right there. There's 2 factorial. They're all there. And then here's even 1 factorial, I guess. 1 factorial. If I can write it properly. No, that's 1 factorial, of course. Usually when you're trying to solve a problem with recursion, you're going to find the next smaller version of the problem. So it's important to find the 4 factorial rather than any of the other ones. But it's good to notice them all. But 4 factorial is what we care about. So that's kind of interesting. Any questions about why that is 4 factorial, why it's there? That's what we notice if you have a recursive problem. If you think it's solvable by recursion, you have to find it inside of itself. So we found that smaller factorial inside of 5 factorial. And this is going to generalize, right? 5 factorial equals 5 times 4 times 3 times 2 times 1. There is the next smaller factorial sitting right there. There's 4 factorial, right? This works for any factorial, right? Here's 7 factorial. That's 7 times 6 times 5 times 4 times 3 times 2 times 1. Do you see how there's a 6 factorial sitting right there? It's always one smaller. So let's do it this way. 5 factorial equals 5 times 4 factorial. See that? And there is a smaller factorial finding problem. That's important. That's what we're trying to look for. A smaller. It's got to get smaller somehow so that it stops. Factorial. Let me draw that over here. Factorial finding problem. Yay, we found one. And this generalizes. 5 factorial equals 5 times 4 factorial. 7 factorial equals 7 times 6 factorial. Do you see a pattern there? You ask me for n factorial. What's that? But n times n minus 1 factorial. See how it's going to generalize like that? That's n times n minus 1 factorial. That works most of the time. Almost all the time, in fact. That's defining factorial in terms of smaller versions of itself. So that's called the recursive case to a recursive solution. This is called the recursive case. Boop. Just like that. Do you see how I wrote that? Does that make enough sense to us? Like, because 5 factorial is 5 times 4 factorial, 7 factorial is 7 times 6 factorial. So in general, n factorial, or n is like 5 or 7 or whatever, is equal to that same n times the one smaller factorial. Does it make sense how I came up with that? That's kind of cool. All right. And so that's called the recursive case. And in addition to that, we need like a smallest doll. We need a place to stop because we don't want to keep running that forever because it'll never stop. We want it to stop eventually, right? We need to add some kind of stopping condition where we know the answer immediately. We don't have to like send it off, throw it off to a smaller factorial problem, right? So the question that we have to ask ourselves is like, when do we immediately know n factorial, which n is that true for, without having to go and calculate like n minus 1 factorial? Or ask the question, when does this rule break down? So let's try it for 5 factorial. Let's try and use this recursive case rule as long as we can. See when it breaks down, and we'll maybe use that as our base case. All right, so 5 factorial, according to our definition, that's 5 times 4 factorial, which makes sense still. And then that will be, we'll go off and we'll calculate 4 factorial with the same equation. 4 factorial is equal to 4 times 3 factorial. And that still makes sense. Yeah, that's still normal. You write it all out. Yeah, that's correct. All right, continuing, 3 factorial, running this rule again, that's equal to 3 times 2 factorial. And still that makes sense. That's still working. 2 factorial, that breaks down according to our recursive case rule as 2 times 1 factorial. And yeah, that works. That totally is normal. 1 factorial is defined to be 1. That's cool. All right, 1 factorial using this rule. What would happen? It's 1 times 0 factorial. And technically in math, 0 factorial is 1. It's defined to be 1. And so this still works if we'd like. All right, let's plug that in. Let's use this rule for 0 factorial then. 0 factorial is equal to 0 times negative 1 factorial. This is where it stops making sense. First of all, negative 1 factorial does not exist. Factorials of negative numbers, those are a no-no. And then also, the second you multiply by 0, the rest of your work goes away, because the whole answer is 0. So we do not want to ever get this far. The rule stops breaking down. Right, it stops working. It breaks down when we try to calculate 0 factorial using the recursive case rule. So we should have stopped before that. All right? So we could just say 0 factorial, just say, hey, if you ever see that, it's 1. Or probably because we've never been asked for 0 factorial before and that's confusing, let's just stop at 1 factorial. Let's just be like, all right, if you ever ask me for 1 factorial, user of this program, then I'm just going to tell you the answer is 1 immediately. I don't have to go and calculate 0 factorial or use this rule anymore. Does that make sense? So that's our smallest problem. Like, we know the answer. Just give it back. That's called the base case. If somebody ever asks you for 1 factorial, don't use this rule anymore because then it stops making sense. Just say it's 1 and call it a day. All right? That's called the base case to your recursion. That because that needs to stop your recursive work. Eventually, you need to stop. Otherwise, you will never stop. Base case. Because you can't like unfold this rule until the end of time. That's the goal. So these two rules together are the recursive solution for solving the factorial problem. Are there any questions about that? If you have both of these, like you asked me for 5 factorial, I use this rule a few times. Plug it in, plug it in, plug it in, until I get to 1 factorial, like the answer is 1, and then just start multiplying the answers back. That's the goal. All right. So, the whole point of this is to make a program that does it this way. So let me show that to you. All right. So let's write a recursive. Recursion is the noun. Recursive is the adjective. So let's write a recursive function because we usually write functions to solve problems for us, right? So let's write a recursive function that computes the factorial. All right. So it's usually functions at the function level when you're writing programs. Those are the recursive things. And a recursive function is one that hands itself the problem, right? It's like, all right, you're calling the factorial function on n, then I'm going to call the same factorial function on n minus 1. I'm going to call myself inside of myself. That's interesting. Right? So a recursive function must call itself because the problem is defined in terms of you. You're the one doing factorial, so all right, go off and do a smaller factorial. So here's what this would look like. Let's make a function called fact, short for factorial. Fact of n. This would compute the factorial, right? Computes n factorial. Fine, n factorial. All right. What do we need to give back? We're asked for the factorial of some n. We just have to figure out, we have to run these two rules. We're either in the recursive case or the base case. We're not sure which one to run yet. So we have to use an if statement to figure out, are we in the base case right now? Is somebody asking me for the factorial of 1? If so, I know the answer. Otherwise, somebody's asking me for a smaller factorial. Right? Somebody's asking me for a bigger factorial, which means I better run the smaller one. Right? So let's see if we're in the base case or the recursive case. So if n is 1, if that's true, what does that mean? N was 1, we're trying to compute, somebody's asking for fact of 1, which is 1 factorial, right? So we're in the base case in that case, and we want to return 1 back to whoever called us. Base case, return 1. And when you return from a function, it stops. So you're all done. It gives us back an answer immediately. Else, right, if we hit this else case, that means n was not 1, and we have some maybe bigger number that we want to run this rule on. We don't know what the answer is for that n factorial yet, but we know that we can calculate it by multiplying our n by the smaller factorial, all right? So this is the recursive case rule now. And here's how you program it. Here's how you program that math expression. We need to give back this. This is our answer. We need to give it back. N times n minus 1 factorial, right? So we need to go off and figure out what n minus 1 factorial is. And we are the ones computing that. So we get to call ourselves. Let's call the result x. Let's say fact of n minus 1. Isn't that crazy? We're going to call ourselves, asking ourselves for the factorial of n minus 1. It will work. Eventually we're going to get down to the base case, and it will build itself back up. And then our goal is to always give back, in this case, n times n minus 1 factorial. So n minus 1 factorial is sitting in x. So return our n times that x. All right, so that's going to be the goal. And the weird new thing is that inside of our definition of this function called fact, we are calling fact, which should make you feel a bit uneasy. It's going to work, though, because it's a smaller call. All right, so that's really, really cool. So, for example, if I were to call fact of 5, I'd hit this recursive case, and it would go off and it would call fact of 4 before it gives back its answer. It'd have to go and put fact of 4 into x. So fact of 5 would go off and call fact of 4, use that to build up its final answer. Does that make sense? It's very weird to think about. But let's actually put this into Python and watch it work. And then I'll try to explain some more why this will work. So, how fun is this? Oops. There's just a stray mark there. So I'm going to open up idle, and I'll make a folder for today. This is one of those rare Mondays where we write code. So this is lecture 27 apparently. And so I'll make a new file in a folder called lecture 27 for us. And I'll call it, I guess, fact.py, because that's the function name we're gonna write here. So there's the code. Let's put it in here. Let's make our fact function, def fact of n. What do we got to do? And the goal of this is, of course, to computes n factorial. Fact of n. What do? We got to figure out if we're in the base case or the recursive case. So if n is 1, that means the user asked us to calculate 1 factorial. That's our base case. We immediately know the answer to 1 factorial. It's always 1. It's defined in math to be 1, right? Otherwise, else, if n was not 1, it's probably something bigger then. So we're in the recursive case. That's the other rule, where we don't immediately know the answer, but we can just like throw it off to a smaller problem. If that one knows the answer, we can multiply our n by it and get the thing. So like if we were asked for 5 factorial, we'll go ask ourselves for 4 factorial, get it back, and then multiply our 5 by that. So recursive case, let's call fact of n minus 1, and we'll save that away in like an x variable. And what we need to give back in the recursive case is always Rn times the factorial of n minus 1, which we asked ourselves to go and calculate. It will eventually give it back. Crazy. So let's ask for the fact of 5. Print fact of 5. And it really will do it right. It does compute 120, which is the answer. And the goal of functions is you can ask it to compute any factorial within reason, and it will go and it will compute them for you again. It's like, all right, 3 times 2 times 1, yeah, that's 6. That works out, checks out. So this is somehow looping in a sense, right? It's a little weird to think about. Fact of 5 is going to call a fact of 4, it's going to call a fact of 3, it's going to compute all these inner factorials until it's ready to give back the final answer. Same with fact of 3, all right? So any questions about this before I draw a diagram that should help it make at least a little bit of sense? This is a bit of a complicated topic. There are some problems that cannot be solved, otherwise you must use recursion. So that is the goal, all right? That's why we're learning about it. So I want to show you a diagram. I want to write a diagram here for why factorial works, all right? It's called a stack diagram, and we call it a stack because it's like there's a stack of work to be done. I can't remember if I showed you this already, but it's just like a stack of work that you want to do. Stack of work. I think I did show it to you when I was talking about print versus return, but let's just redefine it. A stack of work to be done slash, like, it also tells you, based on the order of things, it tells you like who's going to get back the answer to some call. So who wants whose answer. The call right below you is going to get the return value that you're giving back. So, all right, we were out here in our outermost code. Remember all this, and we called print fact of 5. Right? That's the very first thing we did that was useful, that we care about remembering. So we called print fact of 5. So that was the first call, and then so we're inside of print. This is a call to print, and print is like, I don't know what fact of 5 is. I don't know that answer yet, so I need to go off and compute it. So print will call fact of 5 for us. And then that's the new thing on the top of our stack of work to be done. We have to go and compute fact of 5. We cannot go on until we know that answer, because that's what print wanted, right? It's print who wants that answer, so it's sitting below us on this thing called the stack. All right, it's the stack of work to be done by our program. And then fact of 5 hits its code, and it hits the else case, right? Because 5 is not 1. So it will go off and it will compute. It has an x variable. It needs to fill it. It doesn't know the answer yet. It needs to go off and it needs to compute fact of n minus 1. All right? And if n is 5, n minus 1 is 4, it will go off and compute fact of 4. So it needs to go and call fact of 4 before fact of 5 can continue. Does that make sense? Fact of 5 will call fact of 4 because fact of 5 is waiting on this line. It doesn't have anything to return yet. It needs to get this answer so it can put it in its x variable. Okay? So fact of 5 is waiting right now on fact of 4. Now it's fact of 4's time to shine. Fact of 4 is the thing that's working, that's running right now. Right? So there's 3 function calls that have not yet completed. Print is waiting on fact of 5, and fact of 5 is waiting on fact of 4. That's the goal right now. And so now we're in fact of 4. And we're trying to do stuff, trying to compute the 4 factorial. So again, 4 is not 1, so we're going to hit the recursive case. And again, we need to fill in this x variable. It's fact of 4's x variable. It's a separate call, so it's a separate variable, local to the function call, if you remember those terms. And it doesn't know what to put in x yet. It needs to go in, it needs to fill it with fact of 3, but it has no clue what that is. So it has to go off and call itself. Fact of 4 will call fact of 3, and it will wait on this line until it gets it back, because otherwise it has nothing to return yet. Does that make sense? How fact of 4 will call fact of 3 as well. They're all trying to get at those smaller answers, and it's handing off the problem to a smaller version of itself. That's the goal. Eventually it will get down to the smallest version and give things back. So these are a bunch of unfinished function calls. They're all running at once. The thing at the top is the thing that's really happening right now. Everybody below is waiting. All right? Fact of 4 wants fact of 3 stuff. Fact of 5 wants fact of 4 stuff. Print wants fact of 5 stuff. That's what's going on. All right? Please yell at me if you have any questions about that. It is a bit of a complicated idea. And then again, fact of 3. We're up here, n is 3, and we're going to hit the recursive case again because 3 is not 1. So fact of 3 has an x variable it's trying to fill. It needs to put fact of 2 in it, and it has no clue what the answer is. So it needs to go off and call fact of 2. And it's going to wait on that line again. So every call to fact so far is waiting on this line right here. Hopefully it's going to get an answer back eventually. And so fact of 2 is, again, not 1. It'll hit the recursive case and try to fill its own x variable. And it needs to go off and call fact of 1. It doesn't know its answer. So it's going to wait on this line for fact of 1 to complete so it can put the answer into x and continue. So fact of 2 will wait on fact of 1, and that will be the thing at the top of our stack. That's the thing that's trying to do its work currently. All right. So finally, we're in a call where fact of n where n is 1. So n is equal to 1. We are in the base case. We can return 1 to whoever called us in fact of 1. So fact of 1 is going to return 1 to who called it, which was fact of 2, the person below it on the stack, and then it's done with its work. So now we're back in fact of 2. So I should be erasing this, but fact of 2 is really the top of the stack now after fact of 1 returns. It returns its 1, finally gave an answer back. That's the whole point of a base case. We need to stop eventually. And now we're going to build up the answer slowly but surely. All right, so fact of 1 just finished. We got the answer back. It was 1. Fact of 2 can finally put that in its x variable. It's like, cool, 1. Now it can fill that variable. And now it's ready to run its next line. I will return to whoever called me. I'll return my 2, because fact of 2 means n is 2, right? The n for this call is 2, times the x variable that I just finally filled in after all this time. Times 1. 2 times 1 is 2. I'll return 2 to whoever called me. And that was the person below it on the stack. Fact of 3 was waiting on fact of 2. It really just did back, right? 2 factorial. It worked. See how that's going to unwind slowly but surely? Fact of 3 was, again, waiting right here on this line for fact of 2. A bunch of calls to fact. We're all waiting on this line. Fact of 3 got fact of 2 back, so it can store the 2 in its x. And then it's finally ready to run this line now. It can multiply its 3, because it was fact of 3, by the 2 that lives in its x variable. And so that's 6. It'll give that back. That's what it's going to return to whoever called it, which was fact of 4. So fact 3 returns 6 to fact 4, who is waiting on this line for that answer to put in its x variable. It's like, cool, I finally got the answer back. I can store that here. So again, I really should be erasing all this. The thing at the top of the stack is the thing without a slash, right? Fact of 4 is what's running right now. So it just got 6, it put it in its x, it can run this line. It can finally return an answer that is its 4 times the value of its x variable, which it now finally has something inside of. All right, so 6 times 4 is 24, and it will return that to whoever called it. And now we're back in whoever called this code. Now we're back in the original call to fact of 5, who just got 24 back, finally, after all this time. I was waiting so long. All these calls are unwinding, It was waiting on this line for fact of 4 to finish. It finally has 24 to put in to its x variable, and it can finally run this line. It was waiting so long, so patiently. It can return its n, which is 5, because this was called a fact of 5, times 24, return that to whoever called it, which was print, and that's 120. And then print is finally like, oh, cool, I finally have something I know how to print. I know how to print an int. Here you go. And it prints the 120 to the screen. And then that was in the print code. Okay? So that is the diagram of how this stack is like making its way to the base case and unwinding all the way back to the original call to build up the final answer. And this is why this code is actually going to compute the factorial. Are there any questions about that? It's a bit of a complicated topic, but oh man, is it powerful. So yeah, definitely study this code. It's a fun little example, I think. I have my CSCI 41 students still struggling with this kind of stuff. So don't feel bad if it doesn't make a whole lot of sense right now. It takes practice. But it is a very powerful, powerful thing. I can guarantee it. All right. So if we're good, I think that is where I'd like to stop today. So I'm going to talk to you about your final exam, which is happening soon, right? We'll talk about that in more detail next time.